which will actually be problem 3, because I realise that problem 2 is quite hard. I'll leave you to do it yourself. So let's have a look at problem 1. And this is an exercise in how you calculate DNA sequence diversity from a data set. So it's the stuff people do, right? This is done all the time. Of course, these days you have software which spits out the answer. That's always a good idea to know what's actually going on. So let's have a look at how we look at this problem. So here's an imaginary gene in humans, and we have 5 sequences sampled from the population. So this one's arbitrarily chosen here, no reason at all, as a reference sequence. This allele number 2 differs by 1 site, 121. This one also differs by that site and by no others. Sequence 4 differs at 2 sites, which are different from this one, and sequence 5 differs by site 430. So the question is, how do we calculate the 2 statistics, pi and theta w, for this data set? Okay, and the sequence is in total 500 base pairs long. So I want people to shout out. How do we go about calculating pi to start with? We have 5 sequences, and we want to calculate pi. Shout. Right. Okay, so the answer, which is correct, is we compare each of the 2, each pairwise pairs of sequences, count the number of differences, divide by the number of comparisons, and then divide by the number of bases. Is that okay? So let's start doing that. Let's calculate the number of pairwise differences. So we have sequence 1 and 2. How many differences? 1. 1 and 3. Somebody else. You've already done your bit. 1. Okay, then we've got 1 and 4. How many differences? 5. How many differences? 1. Okay, so that's the first bit. Then we've got, which one should we look at next? 3. 3 versus 4. 3. 3 versus 5. 2. Okay. And then finally, we've got 4 versus 5. 3. Now comes the difficult bit for me, which is adding up these numbers. I've never been any good at adding things or multiplying them. So let's have a go. 1, 2, 4, 5, 8, 10, 13, 15, 18. Okay, is that correct? Check me? Okay, thanks. So we've got 18 total number of pairwise differences between all these pairs of sequences. So how many pairs of sequences have we actually compared? No? How many pairs of comparisons have we made? 10. So what's the general formula for that? Well, in general, if we had, say, n sequences, what would it be? Okay, somebody said that n into n minus 1 over 2. So here, n equals 5. So we have 5 times 4 over 2. And as somebody correctly said, we've made 10 comparisons. So we've got 10 pairwise comparisons here. Everybody happy with that? Right. So I'll rub this lot off. We've got 18 differences. So what do? We divide 18 by 10. That's 1.8. I've got that right. And what else do we do? Somebody over here. We've got 500 base pairs in the sequence. We want to get the pairwise difference per base pair. 500. Okay, so it's 1.8 over 500, which is, this is the really hard part of the problem for me, standing at the blackboard. So we divide 1.8 by 5, that's 0.36, right? And then we divide by 100. 5 into 18, let me just check myself, is 3, and 3 over, yes, 6. So that's 0.0036. Is that correct? This is a good opportunity for you to see me looking like an idiot because I've got something wrong. So I do want to be checked. So what do we call this estimate? What's the sort of the jargon for this? Pi. P. Or if you were Greek, you'd call it P. We call it pi in English. That's the standard notation for nucleotide site diversity. Everybody happy with that? Any questions? It's not a hard problem, but it's, I think, useful to see how you actually do these calculations. Okay, so that's one way we can estimate nucleotide site diversity. What's the other way we do it? Okay, so we want to estimate what I call theta W. And what information does that make use of? Somebody else. What do we do? Do we pay any attention to the pairwise differences? What's the number that appears? Okay. So what we do is we look at the total number of sites which are segregating in the sample. We don't worry about how many times that site appears as a variant. We just count the number of sites in that gene which are segregating in the sample. Okay, so let's do that calculation. So what does this site contribute? 1. So note the difference here, we're not paying any attention to the fact there are 2 copies of that variant, unlike the other calculation where we did pay attention. So that's 1. If I can find the eraser, which I've already lost. Okay, so we don't rub out the 18. So we get 1 from this site. How many from this site? 2 from that chromosome, that's right. It's got 2 sites which are polymorphic. And then we've got this one. We get another one. So that's a total of 4 segregating sites. Erase the 4, whatever it was, 430, by mistake. So we've got 1, 2, 3, 4 segregating sites in the sample. Okay, we need another number if we're going to calculate the theta W. Anybody remember what that number is? Okay. Got some real enthusiasts for polymorphism here. So we have what's called A sub k. In this case, k equals 5. So what's A sub k in this case? The other number we need to calculate. Well, we start with 1. What's the next term in that? 1 by 2. Next term? 1 by 3. Next term? 1 by 4. Any more? No, we're done. Okay? We go up to 1 over k n minus 1 if n's the sample size. So now I need some help. So it's 1.5, right? plus 0.33, that's 1.883, plus 0.25, so it's 1.833 plus 0.25, and that is equal to 2.058. That's the correction factor. Okay, that's the magic number for the case we're looking at. So what do we do next? We've got our correction factor, it's about 2. We've got the number of segregating sites, and we know the number of bases in the sequence. So we take 4. What do we do next? I'm going to call it 2, the thing on the bottom, because I'm not very good at doing long division in my head or on the blackboard. The exact answers will be given to you. So it's roughly 2. Since this is biology, not physics, the difference is negligible. So what next? What do we do next? Then we have to still normalize by 500. So it's 2 divided by 500, and that is equal to, excuse me, 0.004, if I haven't got things hopelessly wrong here. So that's our other estimate of the diversity, 0.004. So, and pi, as you may remember, was 0.0036. So this one's a little bit bigger than that one. Why might you get a difference between these two numbers? Yeah. Yeah. Right. Yes. Good. Well, obviously, that you're doing the calculation in a different way. But so in general, the number could come out different. But remember what I said in the class, that if you take the average over the entire coalescent process, over and over again, you would expect it to come out the same. So typically, you don't expect them to come out exactly the same for this particular instance. That, as you said, they're going to be different because pi takes into account frequencies and theta does not take into account frequencies. But suppose this difference is real, why might theta w be a bit bigger than pi? Suppose this was really a statistically significant difference between the two. You might want to think about possible biological causes and something. So what's this model assuming? For theta and pi to be the same. Anybody? The specific assumption here, populations in equilibrium out of mutation drift with a constant population size. So could be wrong. Not be in equilibrium because the population size has changed. It could not be in equilibrium because it's not neutral. It might be in equilibrium, but it's not equilibrium. So there are a variety of different factors which could cause difference between difference between phi and theta on the basis of the assumption of standard curve reciprocity. And if there is, then you say something else again, which is quite a lot. Okay, we've cracked that problem. Any questions there? I hope this was a good way of doing it rather than you all sitting there scribbling. But I'd encourage other people to ask some questions other than these two ladies sitting at the front. Next, for the next problem. Shall we go on to the next one? Or Lindy's got some other problems, which I'm sure are more interesting than mine. So if we can get through mine. Let's see. So we're going to ignore problem 2. The formula 1 over NE equals 1 over 4NM plus 1 over 4NF. To get the effective population size. And so there's two cases I'm giving you, NN equals NF, and where there's a much smaller number of males, but you have the same total population size. And then the second part of the problem is you want to use the formula NE is equal to 4n over 2 plus the variance in the number of offspring. So the second part of the problem is when there's non-Poisson offspring distribution, and there's a huge difference. The variance is 10 rather than 2. So I'll give you about 10 minutes, and then I'll come back and discuss the answer to the problem. Okay? So get out your thinking caps, some piece of paper. Get rid of the booze 1 locus. So NM equals NF equals, what was it? 50. So what's the effective population size in this case? 50, right. So it's pretty obvious it's 50, but we can just go through it. 1 over NE equals 1 over 200 plus 1 over 200 equals what? Sorry, I've screwed up here, haven't I? I should have said 1 over 4NE equals... what am I doing? 1 over 100, okay. Yeah, I was right, sorry. 1 over NE equals 100, NE equals 100, right. Oh, well, that was a bit of humiliation for me. Okay, yeah, so I gave you the right formula the first time. It's been a long day. So NE equals 100. In this case, we have 2 sexes. It's not very different from the Wright-Fisher model when the 2 sexes are equal in number. Okay, what about the other case where we had only 5 males and 5 females? So, same formula. So 1 over NE equals 1 over 4 times 5, right? Plus 1 over 4 times 95. That gets a bit difficult. So that's 1 over 20 plus 1 over 380. Right? 4 times 95, 4 5s are 20, 4 9s are 36, so 1 over 380. So we then have to turn that upside down to get NE. That's not, sorry? Yeah, right. Okay. So it's 19, roughly. Thank you. We do the simple arithmetic here, which is what I'm always really bad at, as you may have noticed. Any questions there? The effective size here is 19. So a lot smaller than 100, right? Refresher question. Does anybody have an intuitive explanation for why the effective size is so small in this case when we've got this small number of males compared with females? Somebody else. You've said enough. Yeah. Right. Yeah, that's part of the answer. The males. Yeah. So the full answer really is that the number of genes which go through to the next generation, half of them come through males and half of them come through females. So half the genes in the population are going through these 5 males each generation, and that's what really pulls everything down. The other half are coming through the 95 females. So it's the small number of males that makes a difference because those males contribute equally to the females. And that's an important principle in genetics. You may learn about Fisher's theory of the sex ratio at one point, where he points out, uses the same principle, explains why the sex ratios of many organisms are about 1 to 1. Any questions there? Nice easy problem, this one, I think, except I got it wrong to start with. Let's look at the last part, where the variance is very big. It's 10 instead of 2. So we just plug into this formula. So it's 4 times, what's the size of the population? I've forgotten now. 100. Okay, n is 100. What do we divide by? 10. Right. VK plus 2 equals 10. So that gives us 4 times 10 equals 40. Everybody got that? Sorry? Oh, 12. Thank you. 4 times, it would have been easier if I'd made it 10, wouldn't it? 4 times 10 over 12, so that's 40 over 12, 400 over 12. So that is something like 12 into 40 is 3, and 6 over 35. So effective size is, if I've got it right here, is 35, not 100. So again, this large variance in offspring number brings down the effective size quite considerably. And there's no reason really why organisms should have a Poisson distribution of offspring number. In fact, there are many biological examples where there's a much bigger variance in family size than with a Poisson. So again, what's the intuitive reason for this? Why does a big variance bring down the effective size? Yeah. So, yeah, I'm not quite sure I caught what you said, but right. Yeah. Yeah. So we're getting a lot of alleles coming from the same small subset of parents, the ones with the big reproductive success. And in fact, there's a generalization of the coalescent process which takes into account very extreme offspring distributions, which makes life much more complicated, and we're not going to deal with that. But there could be organisms where we get a lot of deviation from the standard coalescent if you have a really big variance in offspring number. Okay, good. Any questions there? Sorry? Ah, you're a clever lady. Yes. That's a good point. If we go to this formula, okay, the variance in family size is much less than 2, then you get a bigger effective size. And in limit, if there's no variance, what's the effective size? Twice the population size. So if VK is 0, your actually effective size is bigger. That's actually a principle which is of some practical use. In conservation biology, you might be very concerned about loss of variability, fixation of deleterious alleles when you're just breeding a small number of individuals in a zoo or something like that. And so people take quite a bit of trouble to try and equalize family sizes and remove the variance and make everybody contribute equally. So if everybody contributes equally, that actually doubles the effective population size. So there are situations in which you could have an effective size which is bigger than the actual breeding size. It's a good point. Any other questions? Right. So let's go to the last problem. And switch back to no answers. Right. Have you all got the sort of lecture notes for the lecture I gave handy? Because it's going to be difficult for you to deal with this problem without those. They should, yeah. Okay, so I'll give you some time to do this problem. It's in 2 sections, all based on material I presented yesterday. I'll just give you a couple of hints, get you going. Part 1, you need to use the formula for selection with selection coefficient 0.1, but this is a diploid model. So the formula I gave you, multiply the time by 2. Okay, so you can use the formula I gave you for the time it takes to change allele frequencies. But you should remember this is the diploid case, not the haploid case. And secondly, you should use the probability of survival formula that the survival probability of a new favorable mutation is 2s times h in the case of a diploid. And in this case, of course, h equals a half to make life simple. So if you use those 2 formulae, you should be able to work out the answer to these 2 parts of the problem. Now, this is a bit more to this problem than the previous one, so I'll give you 15 minutes instead of 10 minutes, okay? And then I'll hand you over to Lindy. We'll forget about problem 2. The answer to that problem, you can look at that in your own spare time. It's quite a bit harder than these 2 problems, and if you don't feel like doing it, don't bother. If you do want to do it, the answers will be available later in the course. Okay? Any questions? So have a go at this problem, and see how you go. expected for me to do it on the board, so I'll just walk through the answer with you using this the crib here, which I've made. So the question was, start with a frequency of 0.001 of this dark form of the moth. Hideous air pollution hits it, so it starts to spread. And we're going to look at its frequency after 120 generations, okay? So the formula, we're modifying slightly the one I gave you. We have to double the time up because the model is diploid, not haploid. This time, we have 2 over s, then we have our logarithm function. What's qt? Final frequency of the dark, the allele, p sub naught, the initial frequency of the normal form, q sub naught is the initial frequency of the melanic form, and p sub t is the final frequency of the normal form of the moth. So, by the definition of a natural logarithm, let me turn these lights off. By the definition of a natural logarithm, we take the natural logarithm if we raise this to the power e, we get qt p naught q naught pt, that's this term here, all raised to the power e, or I'm calling x, and so that's equal to the exponent of t, st over t. So I'm bringing the t and the s over to this side, so we get st over t, and then we take the exponent of that. Okay, everybody happy with that step? So we can rewrite the equation again as qt over pt, bringing p naught and q naught over onto this side of the equation as q naught over p naught times the exponent of st over t over 2. And that's the sort of algebraic solution to the problem. Anybody got any questions about that? If you're familiar with the use of logs, not too much of a problem. If you have a computer or a hand calculator which gives you exponents, then we can just plug those numbers in and get the answer. So that's what's done here. You were told the initial frequency of the allele is 0.001. The final frequency is 0.999. T is given to you as 120. S is given to you as 0.1. So S2 over 2, therefore ST over 2 is 6. So we then get QT over PT is equal to QT over 1 minus QT by definition, times 0.001 over 0.99. That's the initial frequency Q naught, and that's the final frequency P sub t of the other allele. Multiply that by exponent of 6.0, we get 1.81. So this is just trivial numerical manipulation of the formula here. Okay? So QT is equal to 0.004 times 1 minus QT. And we can rearrange that by bringing 0.44 times QT over to this side. That gives us 1.04 times QT is equal to 0.404. Sorry, there's a typo there. There should be 1.404 QT. So I got it slightly wrong again, right? So there should be 0.404 over 1.404. It doesn't make much difference. The answer, you might want to do the correction yourself. As I said, I'm extremely bad at numbers. So that gives us the right answer. The the really correct answer is 1.404 QT is equal to 0.404. So QT is 0.404 over 1.404, so it's a little bit smaller than that. So you're also asked what's the frequency of the non-melanics at the end of the process. This is the allele frequency, right? Now, suppose I got the answer right here. The allele frequency is 0.288. What's the frequency of non-melanics? So the frequency of non-melanics is basically the frequency of the homozygotes, the alternative allele. It's not the frequency of the allele. This is kind of a slightly trick question. So the non-melanics are the individuals who are homozygous for the normal form. So their frequency is 1 minus 0.288 all squared, right? It's P sub t squared is equal to 1 minus QT sub squared, right? So we're looking for the frequency of the non-melanics which are left at the end of the process, and that is 0.507 squared. According to my calculation here, so it's about 0.5. I'm not sure where I'm getting this 0.507 from. That's wrong too. So 1 minus 0.028 is not 0.507. It's 1.712. I think I was drunk when I wrote this problem out. The algebra is all fine. So it's 0.172 squared, so that's about, in fact, about 0.5. So at the end of the process, the allele hasn't gone to fixation, it's gone, and we've still got quite a lot of non-melanics present in the population, but still about 50% of the population. That's actually what happened with the spread of the melanic moth. It didn't go all the way to fixation. It went to a high frequency. Now, what happened about 30 years ago in Britain is the industry was destroyed by the regime of Mrs. Thatcher, so all the smoke pollution's gone away. So what do you think has happened to the frequency of the melanics? It's gone down, right. So this is actually, they've really decreased, even in a place like Liverpool, which used to be pretty dirty, there's almost no melanics left, so the whole thing's gone backwards. So it's an example of how evolution can go in one direction and then it can go the other direction if the environment changes backwards and forwards. Okay. So I'm sorry about those numerical errors. I have no idea how they came about. I will correct these errors in the final version of the problem. But it's actually a good experience for you to see your teacher screw up badly, I think. I'm not claiming these are deliberate mistakes. I would be lying if I didn't. Okay, so that's the first part of the problem. Any questions there? It's just simple plugging in to the equation, and if you're not totally incompetent, you can do it correctly. I'm totally incompetent, and I did it incorrectly, so there you are. Okay, what about the second part? It's actually a bit trickier conceptually. Let's walk that one through. So you're asked, what do we have to do to ensure that the probability that a new mutation to melanism would have to, how many times would this have to occur to ensure that there's a probability of 0.99 that at least one of them would escape random loss? It requires a little bit more thought than plugging into a formula. So first of all, what's the probability of fixation or establishment of a single mutation here? All right. So fixation probability, we all agree, is 2hs for a single mutation. H is the dominance coefficient, S is the selective advantage in the homozygote. So H is a half, right? S is equal to 0.1. So what is SH? 2SH. Right. 2SH equals 0.1. That's the easy part. So that's and actually this is a little bit rough, this approximation for such a large selection coefficient, but that's roughly correct. So that's the probability that one of those mutations, a single mutation, survives random loss from the population. As Lindy was explaining this morning, most mutations, therefore, will get lost, 90% of them. So we want the probability, the number of mutations that gives us a probability of fixation of 0.99. So the number we want, let's say, is n, the number of mutations that arise such that the overall probability of establishment, survival of the mutation is 0.99. So what do they have to do in order to become established? They have to survive, right? So you have to survive loss. So what's the probability of loss? We want the probability that of loss of 0.01 of all of those n mutations. What's the probability that one of them gets lost? Well, it's the reverse of yeah. So probability that one gets lost is 0.9. So what's the probability that n of them get lost? They're all independent of each other, so it's 0.9 to the power n. So we want 0.9 to the power n to be equal to 0.01, that's 1 minus 0.99. So, in fact, what we want it to be is actually less than or equal to 0.01. But we can solve for the value of n by setting it to be equal to 0.01. So they're all independent of each other. If one of them has a chance of loss of 0.9, if we take n of them independently, chance all of them go extinct is 0.9 to the power n. So we want to find the value of n which just balances out, comes to 0.01. Okay? So we've got an equation here, 0.9 to the power n equals 0.01. Is everybody happy with that? So it's a simple principle. Each mutation arises in the population, has a fairly high probability of loss, in this case 0.9, and it goes on and on. It's a bit like the coalescent process until one of them survives. And so multiply across all those probabilities of survival, of loss, 0.9 to the n has to be equal to the overall probability of loss. So how do we solve that equation? Sorry? Logs. Yeah. We appear with John Napier again. So we take n times log. We can use log base 10 if we like. It doesn't matter what kind of log we use. Log 0.9, we don't have to use log e here, is equal to log 0.01. And so n is equal to the ratio of log 0.01 divided by the log of 0.9. So that gives us a solution to our little problem. I did it using natural logarithms on a hand calculator. But it doesn't matter what kind of log you use. I make the answer 43.7. Did anybody get the same number as me? Yes? No? Okay, so it requires about 44 new independent mutations to have a really high probability that one of them gets through, moves up in frequency, and is immune from random loss, even with this rather strong selective advantage. So natural selection isn't necessarily omnipotent. There's a random element in the survival of new favorable mutations, and that's quite an important principle in population genetics. Any questions there? Time is getting on. I agreed with Lindy beforehand that we could be flexible, and she was very happy for me to do most of the problems. I can see Deborah waving her stick at me at the back. I apologize for the slight mess I made of problem 3, and I'll make sure you get a corrected version of the answer to you at some point.
Okay, so am I on? What I'm going to suggest is that since we don't have much time, but the first few are completely trivial, as you can see, like make a little sketch, make a function, and I think we can, if I'm going to put this bit on the board here, so this is the probability mass function, right? The probability of having 0, 1, 2, 3, or 4 offspring, and for this organism, those are the only possibilities. These probabilities add up to 1. So I'll put that over there so that you can read the rest of the questions. And what we'll do is we can make it a race. You can just work through. So if you have training in physics, you probably get to the very bottom, even in the 20 minutes, I think. And if you don't, you just go through, and I'll circulate around if you get stuck on something and you have a question or you need some help. And then we'll do the answers in my lecture tomorrow. It'll be a really good introduction to what I want to show you tomorrow. Okay, and the one thing, I did want to talk a little bit about this. When you get to 3, you have to build this function. Maybe I'll move it up. When you get there, oh, sure, thank you. There's this function f of x, and you take those values. You put p0 here, and you put p1 in front of an x, and you put p2 in front of an x squared, up to p4 we have only in this example, right? And you may, it's a bit mysterious the first time you see a generating function. But it doesn't have a lot of physical meaning. It's kind of like mathematicians, we have a huge toolbox of things that we can do with functions. So we like to deal with functions. We like to deal with functions much more than we like to deal with lists of numbers, like I started with the p0, p1, p2. And this is a way, actually, kind of a trick for us to store that list, p0, p1, p2. We kind of store it in a function, and then we can use all these neat things that we do with functions, which I'll show you tomorrow, as a way to manipulate that list. So don't think that f has some kind of meaning or x has some kind of meaning. It's really just a mathematical trick. Herbert Wolf calls it a clothesline for hanging the p-values on. So the function is just a little clothesline, and we're just going to store each p-value there. Okay? And then, but I still think the rest of it will make sense. So first I'll just back it up enough so I can write those numbers up, and you can just start on question 1 and see how far you get.